Hi, I'm Phil Porras, and this is a short description of Malgram's dynamic analysis capabilities. Malgram performs several complementary dynamic analyses to produce a detailed evaluation of what a binary sample does when it is executed, both within the host and over the network. These include system tracing, in which the operating system interfaces are instrumented to report all system changes made by the malicious application during runtime. Live OS probing, in which our monitoring tool runs in parallel with the malicious application and probes the OS for details on the app's activity. And intelligent introspection, where we freeze the app in a VM snapshot to examine exactly what changes it made to the infected host. To conduct our dynamic tracing, we employ Cuckoo, an open-source binary execution sandbox produced by the HoneyNet project. Cuckoo captures runtime changes as they occur and in order. It employs an API hooking scheme to record all the key object accesses that the malicious application performs. It extends its dynamic tracking to all spawn processes produced by the app. It produces a dump of the application's network traffic, captures screenshots and dialogues, and captures all files that the app creates or modifies. In parallel with Cuckoo, Malgram also runs the binary in SRI's SANNet environment. The SANNet tracks changes made by the malicious app by interrogating various OS interfaces. The analysis proceeds by launching the malware and allowing it to operate for up to 3 to 5 minutes. In parallel, our SANNet driver executes a series of forensic utilities designed to detect changes to the host and its system configuration. When completed, Malgram runs Volatility's dumpit utility to snapshot the infected VM for subsequent introspection. The SANNet isolates file system and registry alterations, Windows event log records, new and altered environment variables, new services and auto-run changes, DNS lookups, and listen ports. It also performs a rootkit analysis and isolates network packets produced by the app. Finally, Malgram performs a volatility-based introspection of the infected VM, comparing the VM to its snapshot prior to the infection. VDFuse is used to remount the image that was taken by the dumpit utility at the end of SRI's SANNet analysis. Using volatility, Malgram isolates all changes to the OS performed by the malicious app. These include a comparative assessment of the process list and their associated DLLs, a fine-grained analysis of the file system alterations, open network connection information, and changes to the system services and drivers. While these three dynamic analysis methods overlap in the type of data they collect, they can produce somewhat different results. To understand why these differences arise, and how these techniques combine to produce a more robust dynamic analysis result, let's consider several common challenges that arise in malware SANNets. One challenge may occur when a malware sample incorporates API hook finding logic to avoid executing in environments where APIs are being traced. In such cases, Cuckoo may be detected. However, SRI's SANNet and VM introspection strategies do not instrument APIs and are thus not subject to such countermeasures. More broadly, suicide testing in general may incorporate a variety of environment and runtime tests to determine if the malware is being traced. Here, Cuckoo is relatively more invasive in its alteration of the runtime environment, and SRI's SANNet logic may also stimulate runtime anti-monitoring logic. However, VM introspection is non-invasive, in that its analysis is applied only after the infected VM is frozen. One non-countermeasure related issue is that of transient system modifications, in which a malicious app may create and then delete an object before a snapshot of the host environment is secured for inspection. Here, Cuckoo clearly has the advantage, as it has the ability to record all APIs in sequence. SRI's SANNet polls the kernel for modifications, and our VM introspection logic only analyzes the final snapshot of the infected VM before it is recycled. Malware is well known for employing VM detection as a suicide trigger. For example, Cuckoo employs a VirtualBox shared folder, whose presence is directly testable by suicide logic. SRI SANNet uses standard SMB file shares, while VM introspection does not require alterations to the host. Another challenge in collecting application forensics arises when the malware attempts to alter the host OS to prevent probes from detecting a hidden object. SRI SANNet is entirely vulnerable to this threat, while Cuckoo's API hooking has the potential to see the rootkit set up as APIs are altered. However, VM introspection is entirely resistant to this threat, as it does not rely on the kernel's APIs to detect objects within the infected VM. Resource locking can also hinder dynamic inspection when the contents of an object have been locked such that they are not easily accessible for forensic collection. SRI SANDNet is susceptible to some resource locking attacks, and Cuckoo may also have similar issues when accessing objects. VM introspection is not affected, as it operates directly on the raw VM image. Finally, there arises the concern that malware itself may be fragile in its ability to integrate into the OS. In general, the fewer modifications to the normal operating environment a SANDNet requires, the less likely it affects the stability of the malicious app. Of the three techniques, Cuckoo's API hooking may provide the most opportunity for unexpected malware stability issues. SRI SANDNet is less intrusive, though it assumes an ability to perform OS probing in parallel with the malware. VM introspection is the least intrusive, as it does not require host alterations, nor does it operate in parallel with the malware. Thanks for your interest in Malgram, and please view our gallery for examples of Malgram's dynamic analyses.